Great. So let's start with the second talk of today on something completely different. So I have four ish papers to cover today, and it's not my field. Encryption is not my field. I'm going to do my best. If you know something I don't, please do interrupt and say something. The gist of what we're going to talk about is how to do statistics and machine learning at scale, like that's what Apple and Google do, without revealing users' data. And we're going to say what that means exactly shortly.
Will be about the MLOps?
No. So most of our evening today is going to be about the work of this nice lady here. This nice lady is an absolutely overpowered computer science researcher. She has a Turing Award, a Knus Award, a Gödel Award, and very cool woman. And she invented the notion that we are going to talk about today, the notion of differential privacy. But first I'd like to build some intuition about what the problem is before jumping into papers and math. The problem is that as they say, 21st century is the century of data, of big data. And when you have data, you want to analyze it, and when you want to analyze it, it's often useful to give people access to some source of database, like at Kaggle. The problem is, you try to anonymize the data, you try to replace the identifiers with random ones, right? Replace users' passport number with random digits or something. You try to take some aggregates like mean over data or max over data, but by default, or the natural state of things is that this is done ad hoc, as in the analyst looks at the data and what to anonymize, oh, maybe this column, if you release the data out in the wild, then maybe some other analyst will come up with some clever tricks. And to give you some notion of the clever tricks out there at large, this is a paper from, I think, about definitely 20th century. It's either 97 or 77, but the point is that if you have so you take Cambridge, and you take all people eligible to vote in Cambridge, so they are 18 years old and citizens.
Cambridge in Massachusetts.
That's one. And if you know a birthday, then you have 10% chance to guess that the identity of that person, isn't that uniquely identifies them. If you have two fields, that's 30. If you have an index, a zip code, and it's 70. And if you have and this is some US sort of thing. I don't know what the full postal code in the US is, but anyway, seemingly unrelated data gets you surprisingly high precision. And this is the case across a number of domains. Oops, sorry, I didn't mean to open the paper and scare you quite yet. There was this paper in Nature about privacy bounds of human mobility. The key result was that you have a person, they carry a cell phone, the cell phone can do GPS, right? This person's location history is very unique. As in, you can sample just a few points, and that gets you a lot of accuracy. The keynote result is that you can take 4 points, and that's 90% accuracy across hundreds of thousands of people.
What do you mean by take 4 points and get high accuracy?
I mean that you take my GPS history, you take 4 random points, and you can identify. Yeah.
Okay. You can identify.
Sorry.
Yeah.
I don't quite get the task how we formulate it. So I mean,
if we already know the people and their mobile phone histories,
Right.
then taking 4 random points, we can identify which one of already known to us people.
Of course.
this one was.
What I mean to say is that, like, if you, like, say you are not Google, and say you are, I don't know, say you are the FBI, which, like, you say you are a small FBI, like a small private FBI. And you have a van driving around the city and pretending to be a fake cell tower. So you get samples of people's locations stochastically. Like, you don't know where the person is going, but you have a chance of sampling if that person is around this radius from the cell tower. And what I mean to say is that, if you know, if you see this person sampled there, then you can correlate this with other data. Like, maybe you can actually see the person, and so you have like one. So you have those like 4 points indexed by some unknown ID, and you see the person at one of those locations, and that narrows down your like suspect list a lot.
Could I step back? So general problem that you're trying to explain us that if you like mask. So for example, imagine we have a table about like some data about the people, and you think, okay, this column is really private, this one is private, this one is private, and you mask them somehow.
Yeah.
The problem, okay, as I understand, the problem is it's not enough to mask just some of the columns, because assuming on the other columns you can reproduce this and assume really good.
Mm-hmm.
Yeah, so this is the basic problem.
Yeah, kinda. What I mean to do here is to raise fear, uncertainty, and doubt about data minimization.
Yeah.
As in, like, you don't know what they're gonna do, and maybe they can get something out from the data you supposedly anonymized. And I'm going through a few examples of that, like surprising examples to me at least. And then I'm going to get us a rigorous mathematic notion of privacy. Right. So basically the same paper, but the person travels the subway. Like, we have like, say we have tourniquet data where they entered the subway, where they left the subway, like similar results, nothing to see here. And this same sort of paper again, but with web history. So a person browses website, and what they're saying here, we have there were actually at least 2 papers on that. The first one was 300,000 people, the second is 50,000 Firefox users. We see that we have 50,000 users and we have 50,000 distinct browsing profiles, which kind of makes sense, I guess, as in a person's browsing preferences are quite unique, as in the set of all websites the person visits. But kind of they can strengthen that when they take the 100 top websites. I think it's per person. Yeah, and then like they give us similar results, like if you take top 150 domains per person, then that gives us again a unique identifier. So what this entails is that if someone eavesdrops on the network and sees like what you're doing at a cafe, then they do know, like, they can identify you.
If you have a set of all like internet browsing, I guess, activities, and then they see this particular browsing activity in the cafe, then they can, in this whole set, locate me.
Yeah.
Okay.
Well, like they have. This is inherently a probabilistic process,
Yeah.
so the more data they connect, the higher certainty they have. Yeah.
But only if they have like the data of all the browsing histories and match that to the data of this particular person.
Well,
On
this
the
is.
other hand, okay, you can frame it like this. You eavesdropped in 2 cafes, right?
Mm-hmm.
2 different cafes.
Oh, I have
And if
probability
you
of
have-
matching to the
Yeah.
people to the same. Yeah.
Yeah.
You have high probability that it's the same person in both cafes, and then you can match faces
Exactly. So, like, my basic point with this section is that, like, you can do a ton of data correlation, and you do indeed have a ton of data, like, first point, like, this is not the point of this talk. We are not going to talk about how to collect open source intelligence, but trust me, you do have tons of data, and
It's a good business.
and it's a good business. Yeah, thanks.
This now pretty much everyone, I think, encrypts the DNS requests.
Well, let's just keep that for now.
Well, I mean, that's why they now encrypt DNS requests.
Yeah, great point. Yeah, great point. Absolutely, internet security improved like a lot in the last 10 years, maybe even less. Oh, yeah. So this was like introduction to the problem, and now we open our first paper. We're going to walk through, which is called differential privacy.
This is Cynthia.
Yeah, this is Cynthia. This is the flower woman. So like maybe I'll open this page only. So it's larger. Okay, so here we again this is pretty. This is a research in a field where you have to be kind of precise about your definitions, because many definitions of things in security in general have been proposed, and they have been shown to be weird or broken in weird ways. So let's like.
Okay, we're talking about the terms, yeah.
Yeah. So first we start with the terms, like very lesson-like. Our first idea when we think about how statistical databases think census data, so like government statistics should work like, is that access to a database should not enable one to learn anything about a single person that they would not have learned without access to the global database. As in, you will know about the average person in the country, but you won't know about me specifically. Here, this breaks down subtly, and I'll just work through the example we have here. So, suppose, for the sake of example, that we're trying to hide people's heights. And assume that we have a statistics database which has average heights of women. And we know about a person called Terry Gross. She is 2 inches shorter than the average. And we know the average. Then we know Terry Gross's height. Yeah, so consider that at first everything was fine. We use the average height. Then we learned a piece of additional data that this person is something than the average. Now we know the exact number of space. Yeah.
Zip algorithm, but
You don't have a colonization with the heights.
Yeah. And so
Well, basically we knew that zip doesn't work for privacy, so that's
yeah.
another illustration.
So what I'm saying here, or what the paper is saying here, is that this notion of access to a database does not enable one to learn anything which would not be learned without access. It's an impossible one. Because
the correlation is okay. Without the access to the database, we only knew that Terry Gross is 2 inches shorter and than average already without database, but that doesn't tell us exact height. From database we know only that this is average. Yeah, but kind of combining them, we know
exactly.
Learn the
exactly. Yes. So it's a very simple existence proof. Apparently in 2006 or so they invented an alternative definition, which is kind of subtle. Yeah, I think we'll skip this. Again, some more just background, general. We can think of two sorts of databases. One sort of database is like it's just a CSV file on the internet. So this is what they in the literature call a non-interactive mechanism or non-interactive database, something. And then you have another sort of database which is like an online tool you query, and this is kind of like Facebook ads, for instance. So you might know that you can't, you supposedly can't target a Facebook ad like too tightly, too accurately. You have to target it to at least this number of people. So this is a sort of an interactive tool. It limits the number of information you can learn.
What is the interactive component here? So compared to like an API.
It's an API.
Like what is the API? What do we query?
Okay, I see. So like in the case of the of Facebook ads, what you essentially get is if this so like you can restrict the group you're targeting by demographic factors like say age, and then you can also restrict by say their income and so on and so forth. And the API either returns true if this group is large enough or false if this group is too small. So that's an interactive tool. Yeah.
It can be kind of pose it as a reinforcement learning or something situation. I mean, in the case of CSV file, okay, you have all the information at once. Okay, it's all in the file. You have all of that and nothing more. In this interactive tool, okay, you query it, you get the results, the response, then you can rethink and query again, and it responds you something else, but you can compare and infer and alter your requests to extract probably additional information that you weren't supposed to extract.
Yeah, that's it exactly, but
I mean, kind of the database tries to hide something from you, but you can interactively think for yourself and try to extract more than you're supposed to.
Yes, but like two corollaries from what I was talking about. Like first, non-interactive databases are like trouble, as we learned above. As in, it's hard to predict what they're going to do, how they're going to correlate data, and so results for at least in 2006, I'm not sure what happened since then, results for non-interactive kind of anonymization were not good. But
Sorry, can I ask a question? Yeah, so it's very interesting question. For example, you have this CSV, any kind of database, and if you are like mask some of the privacy data and make the distribution differ, it's not so make sense to use it.
Exactly.
Yeah, that's all. If you want to do this.
Yeah, that's absolutely the problem why there are like why the literature isn't very good, because they are struggling with that trade-off about having the data still useful and preserving the privacy. And as Sasha was saying, when you have an interactive tool, like on one hand, the person tries to think of a query which will like yield them something juicy, but consider also that like the other side, the tool can also notice what the analyst is doing, and at some point refuse to answer. And this the CSV cannot do. And like what you can do in practice is like well, what we're going to define later is we give an analyst a privacy budget. Like we say, you have 100 privacy coins.
Social credits.
Yeah. And if you use too much privacy budget, then you don't have access anymore. Like that's it.
That's why everybody hates Facebook ads.
Yeah, absolutely. Okay. So I think okay. So this is. Like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, this is the case of the CSV. So, like, we're not going to cover this really, but I just want to showcase something that so like we're going to cover a bunch of papers tonight, as I said, and this is a 2006 paper. You can see this because it's like it goes like a privacy breach is described by a Turing machine which takes a vector string, and this vector string has a particular entropy. And we model our system as a number of communicating Turing machines, so on and so forth.
We have a lot of these kind of abstractions there.
I'm sorry.
Yeah.
I haven't noticed when they stopped writing like this in each year, because like I don't know, I see. That's subset of papers I read, but they're all like that.
It's a generation change. New authors prefer not to mention Turing machines, probably.
Yeah, I mean, okay.
Sure.
And another way we can say that is that it's like a classical computer science paper, right?
Yes.
Okay, so this will also skip. We'll cover this in the other paper.
My question stands like,
Yeah.
which papers are not like that?
Well, we'll see in the next paper.
Okay. So this kind of community kind of dropped that language.
Well, I guess the dominant approach changed to proofs, yes, and the reason actually in this particular framework in differential privacy is because what they used to do, they used to have like now they embedded what they're doing into a probabilistic framework, and so it just makes more sense to work with these probabilistic tools. And like so, they used to talk about entropy, so like in encryption language, and now they talk about probabilities. That's a kind of paradigm change, maybe. Okay, so here we introduce the thing we're going to talk about the rest of the evening. What we used to have was like a for-all quantifier, like a strong guarantee that auxiliary information cannot cause a privacy breach. And what we're doing to make progress is to make this a quantitative statement. As in, we're going to give a particular bound on some likelihood. And let me see. Yes, we do have
breachiness likelihood.
Yes, let's go with definition. Yeah, actually, I don't like this notation.
Can we return?
Yes, I just wanted
to
to
that introduction.
yeah.
From that paragraph, it looks like again they changed the notion that it's not that now we can learn first kind of the promise which is cannot be fulfilled, that you cannot possibly learn anything about particular person given the database and given the other you have other data. Now we don't promise that, but we say that okay, whatever you can learn about the person from the database and whatever else you learn, it's not because their data in the database. Even if their data was not in the database, you would still learn that thing. So kind of database adds nothing to your notion.
Okay.
Yeah, this is great. Thank you. Yeah, so like what we're doing is we are reformulating the question in terms of, in some sense, like the person's first-person view, as in, should I participate in some survey or not? It doesn't matter, because whether I do or not, the survey, like the database is constructed in such a way that like my particular choice doesn't give me additional risk. So like if my data is collected in this approach, this does not entail additional risk for me.
Okay, but what is about like a medical database? How they guarantee this? Because
yeah, like exactly the thing we're going to talk about next. Yeah, so key point here, no could.
There are two questions. First,
Yeah.
what to do, the second, how to achieve that.
Yeah.
So
Yeah.
we
Yeah.
kind of realized what we want to achieve now.
Yeah, so
Second
first we have like a definition which I promise we can make progress on, which is nor could the disclosure be avoided through action or inaction on the part of the user. Yeah, like we will need this formula, but I don't like the letters they use here. Yeah, let me get my plan.
Create a new one.
Yes, it's just that we'll have the right notation in the next paper. So, okay, this sort of thing is actually useful, I guess. Yeah. So let me get my. So let's go with it. Right. So, what have we here? We have two data sets, D1 and D2. They differ in at most one element, which is to say I either am in the database or I'm not in the database. And we're saying here, I will rewrite this. We're saying that the not nice marker. We're saying that the probability that let's go with f function on data 1 belongs to belongs to s divided by probability of same function on that set 2 it belongs to s is bounded by this term. This is what we're choosing. This is this epsilon here. So, what does this say? Is that we have some analytic query, like average height, something. We have two data sets, one where I'm in, one where I'm not. And we're saying that, how do you frame it? And we're saying that the probability of basically this aggregate statistic having a particular result is bounded by this constant here. And they say it's they don't like fix the value, but they instead say in S because this is framed as in terms of me belonging to some set. As in, they want to learn if I'm in S or not.
Can you give an example in terms of height? As
Well, maybe zip codes, right?
whatever.
Zip codes bound these people into buckets, right?
It's the formula is not clear to me. So, for example, if zip codes, whether I'm not or I'm in the data set. So, what does it mean that this probability divided by that probability is smaller than epsilon?
Yeah, I think I get the question, let me. I think I have a particular example in this.
Oh, it's an exponent of epsilon, so it's close to 1.
Yeah, but it's a fraction.
Oh, wait, what?
Yeah.
Yeah, okay.
So, would you like an example, or do you like?
I think it's clear. Okay, I thought that there's almost 0 on the right, but there's almost 1 on the right. So like the probability doesn't change a lot with this change to density.
Yes. So what this is saying is that whether I am or not in the database, the probability doesn't change. So
Maybe it'll be a little bit more clear if there's like
another way to say it is that like these are almost the same, right?
Yeah.
But why they won't compare just with one, the exponential in the sum?
We'll get to that.
Yeah, okay. So they want to regulate adjust this thing because of this parameter?
Yeah, like like the epsilon is our privacy budget, kind of.
Ah, okay, yeah, got it.
Right, and exponent is just there for like.
Okay, I nice.
Simplifying the proofs.
Because the proof is nice. So like this is the basic construction. What we defined here is that in the slides kappa and on the whiteboard f. F is a randomized function which gives epsilon differential privacy. So epsilon is the privacy budget. This is and then we can talk about whether a particular function is satisfies this definition. And also another thing we have here is that we can generalize this. Like say we have a group of individuals which have some attributes. I don't know. We have the hack space and we have how many liters of club matter are consumed each day. And they might be concerned about, again, correlation attacks when the individual data would have been fine, but if they collate it as a group, then they get some correlation which reveals additional data. And trusts us, the author of the paper, and me, that you can expand this definition to bound, to make this bound exponent of epsilon c, where c is the group number, is the count of people in the group.
So the budget is proportional by the group size.
Yeah, exactly. And notice that this is kind of intuitive because, if you are talking, because this means that this basically breaks when the group is large, right?
Mm-hmm.
This makes sense because when we want to have statistics about the population or about city-wide statistics, then we actually want to have this in the open, right? As in, we do want to have normal data for people's average height in the country, and this is why this definition breaks for large groups. Right. So now we develop additional machinery now to talk about functions, functions can be pretty much arbitrary. We can count rows, we can get averages, we can get conditional averages, we can do histograms, whatever. Don't care. I guess we're going to what you're going to notice here is that if a query is one shot, as in it's just count the number of rows, then it's one thing. And if we have essentially multiple queries, so get this data, then if this, then second query, then this branch, else other branch, then we kind of a smart adversary could use this to infer something if it just gives them the true results in the if condition, because the if condition will leak data. So we have to define some notion of kind of composition for queries to the database. Okay, and now we continue to develop our machinery for constructing these functions. For that, we define the notion of the sensitivity of the function. What sensitivity does is we take the function on dataset 1, we take the function on dataset 2, we get the absolute value of the difference, and we get the maximum such difference over two datasets. So, supposedly, if I'm in this dataset but not in this dataset, the maximum difference will be at the point of divergence, and so this is the maximum value, the maximum absolute value by which this function can deviate. We call this sensitivity, or maybe this would be L1 sensitivity because it's absolute. You can also define L2 sensitivity by its value. Okay, And the next thing we notice that for many useful queries, this delta f will be small, because counting queries naturally have, well, just go with it. No.
So I think it
yeah.
reminds me of the distance between manifolds. Did anyone can reformulate this problem in the terms of manifolds? Differential geometry instead of differential
Hausdorff distance or Chamfer distance.
Yeah, something.
I'm pretty sure someone has. But well, no. Okay, let's just continue with introductions now. So like, the counting query naturally has sensitivity at most 1, because like if I don't belong to that query, then it returns like say 55. If I'm in the query, 56. So sensitivity at most 1. And it is also like an interesting theoretical consideration that sensitivity of the function as we defined it is a property of the function and not the database, because we are confined about over all databases.
So the function average, in theory, has an infinite.
Yes. Well,
I'm sorry, but I'm not understand why it's like condition, not condition, but why it's related to the function but not to the database, this sensitivity. Because, for example, if we imagine that it's like your
okay, so you can define like a stronger sensitivity if you talk about particular databases, but what we're doing here is we're saying for any sort of database.
okay.
So like we are talking about kind of the type of the function, as in we take the worst case absolutely possible with this function. That answers your question?
Not that's you could continue.
So if, for example, like the height of people is within like a sensible range of, I don't know, 0 to 3 meters,
Yeah.
but in theory the database may not have limitations, so you can push a 1,000 meter person in, and in this case, this function, like this theoretical case, this function has infinite
Okay, the function
sensitivity.
has no power there.
So it was my intuition behind like if we don't have limitations on databases, then this is what can happen.
Yeah. So like let's try to go on with this absolute worst case possible with like any database which could happen. Okay, and now we design like our first privacy mechanism. And what we're going to do is we're going to compute the true value of the function and add some noise. And our noise will be symmetric exponential. So this is Laplace distribution, I think. So like this is exponential and this is symmetric exponential about some mean. Oh, so, yeah, this is. Yeah, so let's try to get back to our earlier definition and substitute. So what we're saying here is we take a particular response of the perturbed function R, and we say for all possible responses, the probability that we get this particular response on that set 1 is less than or equal, we get this result on that set 2, multiplied by exponent of this is I think this is exactly our sensitivity from web. Yeah. But this is not absolute sensitivity. This is not over all databases. This is over this database.
Yeah.
These two databases divided by the variance of the noise.
So if I understand correctly, the f is the deterministic function, and the kappa f is distribution.
Yeah, well, like in this paper they call it mechanism. So a mechanism is kappa f is f of x plus noise.
Yeah.
Well, I use a different notation for noise, maybe. Yeah. So in this case, it's actually it's
The Laplace distribution centered at 0.
Laplace 0 and
This is sigma.
okay. So this we just substituted by definition, as in we took the definition of an epsilon differential private function, and we substituted, and yeah, and
So we know which epsilon we need to achieve, which sigma we need to achieve. Epsilon differential privacy.
yeah. So I just like to go through the proof in a little more detail. So first we substituted. We went through that.
So we already assumed that kappa f is epsilon epsilon what?
No, we are
say
proving
that
this now.
Kappa
okay.
f is like that, like function
Yes,
plus
so
noise, and now we ask, okay, how much noise, how much sigma we need to achieve epsilon.
Yeah.
Differential privacy.
So we just define kappa as on the blackboard, then we substitute into the definition, and we notice that
By definition of what? Definition of the Laplace distribution.
the definition of differentially private function.
Oh, so we don't have this proven. This is something we just express for now.
Yes, we just take the definition of differentially private
Okay,
function
okay.
and substitute kappa.
Okay.
And we notice that that the right-hand side has a bound. As we said, this is so this is particular sensitivity, and it is always less than or equal to maximum sensitivity. So this is bounded by delta f, and sigma is sigma. So yeah, this is at most exponent delta f divided by sigma, and this is an inequality. So like we have like we have a bound here, and we can first notice that we can prove this this theorem over two sets, where we take D1 as an empty set, and we take D2 as a singleton set where only I am, and it is sufficient for us to prove this for this case, because others follow.
Because what?
Because others follow from. Not actually sure from what exactly they follow. They follow basically by induction, because our definition is stated in terms of data sets which differ in at most one element. So it's sufficient for us to prove this for an empty set and a set with one element.
Then go on from that and the. Okay.
Yeah. Okay, so we went through this derivation, and we can notice that to get epsilon differential privacy, we must choose a particular sigma, just by rearranging the terms. And this gives us like a general intuition for how this framework works, for how this like for how we think about computations, I guess, in this framework. When we have a particular when we have some class of functions, and we design a mechanism to make those functions private, epsilon private, then we have a particular bound for the noise we must add to the outputs. And this is different because functions can be different, like they can be numbers or booleans or whatever, but this is the general framework. And to give another view into this, so consider a histogram query. So just to remind you, a histogram is a plot like that, where we have like, I don't know, zip codes, so Z1, Z2, and this will be number of people living there, and we have like this bar chart, right? So this is a histogram.
One of the parameters of the query is the bin size. So if we have a bin size of 1, then we get like the perfect distribution, so we know how many people on each zip code there are, and this is undesirable to let people know how many people are on each zip code. Or is that okay?
Yes, undesirable, but we'll frame it in a little bit different way.
Okay.
Yes, we have like a parameter k of classes. So we are not talking about the bin size here. We're talking about the like target number of classes, some particular k, and notice that I can compute this histogram by querying like select where z1 and get this number, and so on. If we just take our prior derivation, then we would have to have so we have to multiply the noise by the number of queries, right? This is like another kind of key thing here. So, like, our naive bound gives us noise. Actually, it will be small O, I think. So noise in the order of k epsilon. But if we analyze the problem in more detail, we notice that in the case of histogram, if I'm in the database or not, only one cell will ever change, and so we actually need less noise. Yeah, so we can actually add the same amount of noise as we used to. So it will be like in the order of epsilon. We just stripped multiplicative term. And like this is basically what the field is about largely. It is about finding I guess this is what cryptography is about largely. It's about finding clever shortcuts to not add noise in this case. Yeah, just a little bit more ground to cover with this paper, and then we'll take a break, I think. Yeah. So when we have this notion of queries in sequence, we can think about adaptive adversaries. So an adversary which can try to make life worse for us. And so you take a vector of query functions, and like this was saying is that, so we take the sensitivity of a set of queries to be the largest sensitivity in this set, and then we probably don't have to go through this derivation now, but basically again just by substitution we can say for a set of queries, the same Laplacian noise mechanism we designed earlier gives a maximum sensitivity divided by variance differential privacy. Okay.
That's why they need exponents. Needed exponents.
Yeah, exactly.
Because they turn products into sums.
Yeah. Okay, so that was one paper. I kind of have 1, 2, 3, 4 more to go, but it's pretty late already, so we probably don't want to cover that today. So, did you get the basic notion of differential privacy, like what it essentially is about, kind of, sort of? Okay.
Plus minus.
Great. So I think what I'm going to do is I'm going to postpone additional dives into differential privacy with more math and more complicated composition theorems and additional smart shortcuts for maybe another day. And what I will talk about now instead to fill another, I don't know, 10, 15 minutes until 9 when we can all 9 is the time for kids to go to sleep. Yeah, so I'll just talk about some examples where I'll give you an intuition about how this all translates to deep learning, and then we'll do it more rigorously another time. Okay, so what we started with was the notion that statistics are useful, but you can break them. And again, I want to do this again. Deep learning is useful, but you can break it. And we sort of discussed it the other day, but what example I want to give you? So let me give you an evocative example. It was in the news last year, in year 22, I think. The Apple child porn debacle. Yeah, anyone heard about Apple and child porn? No? Okay, that was American news mostly. So what was the thing about? Some legislative body in the US coerced Apple into scanning messages and device content for child porn because kids are in danger. And so maybe you can see some concerns with what's the usual way we use deep learning models? We deploy them on some beefy server with V100s and run a classifier. Maybe you see some concerns with transferring whole message histories and device data to some absolutely secure government web servers which hold collectors editions of child porn to compare against. Yeah, so what Apple did was to do this machine learning on device. So they trained some model, they distilled it, quantized it, whatever, made it run on the phone. Yeah, I'm actually not sure what happened in the end. They, I think, started deploying it, then I think it's optional now. Yes, I think you can.
Sorry, but it's a text analysis or it's image analysis?
It's image analysis.
Okay.
Yeah, so they have an image classifier.
Yeah.
If you enable it in settings, it can say this is bad content.
Yeah, okay.
you got. And this is so great so far. This is actually great for privacy because we are running the model on device, and this is a nice engineering win for Apple. But let's think about potential misuses here. So if I have this model on device, then I essentially have its weights, right? So I have the model, I can do what I want to do.
Actually, no. Unfortunately, yeah, we faced with this problem in our company. it's not so you could gather the weights. Yes, this is
Mhm.
true. But the code that run like pre-processing, post-processing, you couldn't gather it. This is the problem there. And for most of the model, it's not like that easy to reconstruct this part. That's why it's like you need like high level of engineering and also
Lots of
efforts.
reverse engineering.
Yeah, that's why it's possible, but it's really hard.
Yeah, thanks for that.
In theory, you have the code too because it runs on your device. So
No, it's compiled and not functional.
Reverse engineering.
No, I mean,
Yeah, let's go.
you have to reverse engineer it. Besides, well, although they run it on the GPU, they're most likely or
Yeah, you can make it
processor,
trace it.
and the architecture probably isn't very public. Though on the other hand, it's probably reverse engineered already to some degree because
They have their own framework to run network, and
Sure.
it's closed.
Yeah, well,
you don't care that much about framework. You definitely you have a lot of baked-in functions. I mean, hardware implemented functions. So the kind of assembly code or binary code you run on this GPU or whatever tensor coprocessor is pretty high level. So you can kind of easily or more easily.
Great points on both sides, but let me please just finish that so that like we can switch to peer-to-peer discussion fully. Right. So. And that's actually a pretty good chance that I'm going to be paid for AI AI reverse engineering shortly. So
But I think the kind of upshot of what's coming next is that you don't need to reverse engineer it. You need to run it kind of willfully, giving it your data, and then you can run this adversarial learning or adversarial attacks on that and see what it considers child porn.
Exactly.
And then kind of make child porn doesn't look like child porn.
Right.
You can do that.
So that's exactly what I'd like to cover. So like first stage, let's consider that we have this model because they actually gave it to us. Okay, maybe Apple didn't give it to us completely, but say we have like an Llama or another like open source AI model, whatever.
Yes.
So like we have the weights, then we can optimize with gradient descent for inputs which it will like consider, which it will classify as we want. So we can generate adversarial child porn, or even better, we can reconstruct the original child porn used for training the model.
Yeah, this is possible actually.
And again, like no papers this time because we don't have the time, but there are papers on that. Yes, like if you have the weights, then things are very much possible. But like the next case, I'd like to make my statement stronger and talk about the case where I don't have the weights. Like say I have an API and what I'd like to do is I'd like again to query the model in some way to one task is to generate adversarial examples which will make it misclassify or something, or like misreply, and the other task is to elicit training examples. And
Gather a training data.
yes, maybe it's proprietary, maybe it's child porn.
An example is a classifier that determines whether there's copyright content on an image, for example.
Great point. So if you have a classifier which says if it's copyright or not, then we can pretty good, obviously find the copyright data. And this is actually exactly what I was talking about earlier when I was talking about leak through the if condition. So this was sort of rough intuition about how this sort of problems appears in deep learning setting, and you can apply differential privacy there, but I'm not going to tell you how today. Thank you.
Kind of
great question.
About the
Should I stop recording?
Let's continue.
about the how the whole Apple iCloud CSAM detection thing
Yeah.
ended. They pulled the plug. They didn't proceed with anything. The only local neural nets that are included in the messages app as of right now, as far as I'm aware, is one that detects basically dick pics and other stuff on devices enrolled in like the child profile. So
I'm pretty sure I have this as an opt-in setting on my iPhone, so I think like it can be enabled generally, but yes, I agree with the general point.
CSAM detection.
No, not CSAM, but dick pic detection. Okay, dick pics are certainly not as interesting to do.
I have three questions. As I correctly understand, any of data, no, I mean the big data of any people or any persons, we can mask any part of them or can mask any other parts, but in future there can be any researcher that can investigate another part of data and find some
correlation, some
correlation.
additional,
Yes.
Yes, yes.
Okay. Second point. If some correlations can be found in any of data, it's not it's not influence for me that I make the some researchers poll or voting or not. In any cases, any researchers can understand what I am.
Well, not exactly. The notion that we introduced here was that it gives the data that the researcher can infer. Like, we are not saying that they can find you or they can't. So we are not saying what number that is. We are just saying that the number doesn't change whether you participate or not, like whether your data is there or not. So yes, essentially what you said, yes.
So okay, but maybe he can't understand who am I, but the kind of data will not be changed if I think that I shouldn't vote or make this selection.
So the researcher does some analysis and gets like a probability that this data is you, like say 70%. And in the world where you did vote, it's the same as in the world you didn't vote. It's still 70%. So like what you did or didn't do under this definition doesn't make a difference. The researchers' outputs that don't change.
So I cannot change this sensitive of information in this data.
As in, in some sense, your data isn't sensitive anymore, because if it's processed with these mechanisms, it doesn't give research additional data about you specifically.
So how actually they prove that, for example, your data in some data set, and they said that it's actually not important for us because it could be proved with other data. How they actually prove it?
They
So yeah, so they like simulate it. I mean,
That's one option. Well, that's like one extreme, right? We don't actually
So they not
say you
create
have
something-
0 people in your data set, and you
Okay.
still you just kind of run this random draw from normal distribution and return it
So
as
what
a,
they want,
as an
I
answer,
just want
right?
to make the general assumption. What they want to say in this paper that they try to prove you that your private data is not private. That's is the case.
Well, kinda.
Yeah, they try to say that oh, if we have your private data, but actually everybody has it. Doesn't my database.
Okay,
Well,
maybe,
Why?
maybe in this
like
case,
how you came up to this conclusion?
Yeah,
I don't
I
see the
came up to this
relation.
conclusion because it's what
in
is
this
this
case,
paper about.
if we have some situation when all data can be find about me and we have no privacy, maybe we should not think about this.
Right. So like, what this is about is that we say that if we process the data in a particular way, then there is actually a theorem about this. Like, so, like the thing that we care about, what we are like minimizing, is the chance that a researcher will identify us uniquely, right?
Okay.
And what we are doing here is we are bounding this probability. We say that the probability that if I give the researcher my data, the probability that he will find me is less than a particular number which includes epsilon.
Okay.
May-
And it should be a small number, of course, obviously.
Yeah, I just don't have like this cryptography background. That's why it's a bit hard for me to understand some of the concepts.
Well, we don't have to. And again, I think that's useful to keep in mind the setting what we are talking about, and that brings us to your initial question in the start of production. So we consider this situation that okay, Facebook have all your data.
Yeah.
They have it, but we still consider this private. What we want to prevent is leaking this data from inside Facebook
Yeah.
to run those over the
Somewhere.
internet.
Yeah.
To other companies. So while one company, Facebook, having your data, we still consider this private in this situation, in this setting. So that's okay. Like,
Yeah.
right. When everybody can learn everything they know about you,
Yeah.
that's no privacy.
Yeah.
And we are preventing this situation, data leakage
Okay.
from this source, from the database.
That's
to
a
other
great point.
parties.
How we can prevent about another company?
Like this, via random noise. So we don't let
So
them.
Facebook
ask-
know about me everything.
Yeah.
How I can make additional noise to this data? Or you mean the Facebook should add additional noise?
Yeah.
to-
Facebook ad.
So
noise.
they add additional noise to decrease the probability that they and the other company identify you with this noise.
Yes.
If they leak.
Exactly.
Yeah, if they leak.
No, it's not leakage.
But
Okay.
if they query some.
Kind of the business of Facebook, yes, they give some information, aggregate information to other companies. Well, if they close this up, like encrypt this and don't give it to anybody, or just burn all the data, that would be totally private, okay?
But they
Like,
won't,
no question,
have
like, no
money
problem,
from the
right?
outside.
Yeah. So the problem is, we still have to give some information, aggregate information to other parties, but we want to keep this information aggregated and prevent other parties from identifying particular records in the database, particular instances, particular people. This is the tension, this is the problem. Because running aggregate enough, I mean, it's again kind of beating people into the buckets. And we have aggregates about like set of all people in the city. That's not very identifying. If we have in one district, that's kind of more identifying. If we got the information in one house, that's dependent on how many stores and how many people live in this house. If we got aggregate on the set of one person, one element, this is total de-anonymization, yeah? So we want to kind of bound this thing so you don't learn two small sets.
Yes, this is
People, two small aggregates.
This is great discussion, and thank you about talking about like Facebook accidentally leaking identifying information. So yes, this absolutely applies to when we want like a large provider to give useful information to researchers, but not too much information. But also, I'd like to extend this to like my kind of personal choices. So my iPhone sends a bunch of statistics to Apple. But before that, before it gets uploaded to the cloud, it adds noise with these mechanisms. And so this is done on my side. And so this is kind of my choice about how I'm sharing the data. And why this is useful is like consider urbanistics, so city design. It is very useful to know how people move around the city. But it's like we want to not have the 4 points problem, so we derive appropriate bounds and add noise on device, and then like nobody has the 2 points because they're not there.
You know, this
Java and military bases, sorry.
Yeah, actually,
You know that? Fun story, yeah?
interesting that, for example, if with one storage of data, yeah, okay, this is one example. But for example, yeah, we would imagine that we have the same data about one person in the multiple
Yes,
different
again we can try to
databases.
correlate, right?
Yes, and if one of them guarantee exact percentage, so multiple of them, yeah, you could aggregate. So they need to somehow initiate communication between each other and make like these assumptions based on their probabilities that it's not increased bound.
Yes, this is a great point, and like we'll talk about exact bounds for that next time. But like the overall thing here is that yes, naively we get the worst bound across all databases.
Yeah.
Yeah, but yes.
Okay, so I think we can stop the formal part now. Thanks to everyone for attending and for the discussion. It is great.
Thank you.